To illustrate the process for finding a term symbol for an atom, specifically a larger atom than helium, I want to go through an example where we're going to treat carbon. And I'm going to try to do this slowly so that you can follow what's going on, because I think it's very instructive to see how this is done. So let's, starting with carbon, we know that the electron configuration for carbon is ordinarily something like this: 1s2, 2s2, 2p2. Okay, now I've mentioned that whenever we have a filled subshell, we don't really have to worry about those, because all of the m sub l and m sub s values cancel each other out. So we end up with everything down here having total L equals 0, total S equals 0. So these are in a sense, a good foundation, but we don't need to worry about them. All we really need to worry about here are the 2p2 values. Now, we'll note that since this is a p orbital, we have L equal to 1 for each of these electrons. So for each of them, m sub L has the possible values of -1, 0, and 1. We also have possible m sub s values of plus or minus 1/2 for each of the two electrons. All right, so when we begin to combine these, a good way to go is to look at what the possible values we might get, sort of possible maximum values for the various projections of the total system, because that will guide us in determining sort of what we're looking for. So for the fact that we've got two p electrons, we can have m sub l values, the maximum of which would be if both of the little m sub l's were equal to plus 1. So the maximum value would be 2. All right, now what this means is that the L values that I will need to worry about are the ones where L is equal to 2, but I may have a case where I have m sub L equals 1 and one m sub L equals 1, one m sub L equals 0, so then we would have the possibility of L equals 1, and we could also have the possibility that they cancel each other out, or they both equal to 0, in which case L is equal to 0. This L, which kind of represents, if you will, the magnitude of orbital angular momentum, never goes below 0. It's always a positive number. So these are the three possible values that we're likely to see. What about for the spin? Well, m sub s, if these spins are allowed to be in different orbitals, then they could both be, say, spin up. So the maximum value for this is going to be 1, which means that our total spin can either be 1 or 0. Okay, it can't be, again, a negative value, because we're talking about a positive length, if you will, of the spin angular momentum vector. So this gives us a clue that we're looking at these types of elements in our total angular momentum. All right, we've got L values that can range from 0, 1, and 2, S values that can range from 0 and 1, and we're going to be able to categorize these based on the m sub L values. So when L is equal to 0, m sub L can only equal 0. When L is equal to 1, m sub L can only equal -1, 0, and 1. And when L is equal to 2, m sub L can only equal -2, -1, 0, 1, and 2. And we'll get to these values by adding up the different individual electrons. Similarly, when S is equal to 0, I can only have m sub s equal to 0. When S is equal to 1, I can have m sub s equal to -1, 0, and 1. All right, so when we have these three values, I can assume that I have an S equals 1 state, and when I have just ms equals 0, then I have an s equals 0 state. Now, the j values can range from the absolute value of the difference between L and S. Well, I have different values of L and S here, so the minimum value that I could possibly get out of this would be 0. It's got to be a positive number. The maximum value is something that I would get from the maximum value of L, or 2 here. The maximum value of S, 2 plus 1, is 3. So I could have values that range from j equals 0, 1, 2, or 3. And sometimes one writes those actually in numerical order. All right, what I want to do is show how one would construct these term symbols by basically putting together all the possible microstates. That is, ways that we can distribute electrons into the two different p orbitals that we're going to use for this part of the carbon atom state. Now, you'll note that there are many ways that we can fill 2 electrons into these 3 2p orbitals where I only have 2 electrons. I can have them be both spin up. I can have one spin up, one spin down. I could have them both spin down. So there's a lot of different possibilities. What I'm going to do is I'm going to create a table. And I'll try to do this very carefully and slowly. But this table is going to specify all the possible ways that I can do these. Now, one little notation I'm going to use is I'm going to let m sub l, just the number, be representing which m sub l state it's in, and then I'll have a superscript either plus or minus to indicate which spin state it is in. So, for example, if I had 1 plus, this would be a state where ml is equal to 1 and we have spin up, or plus 1/2. If I had 0 minus, this would be m sub l is equal to 0 and it's spin down. All right, so this way we can, I shouldn't have put an underline over that, I'm circling it. So this is one way we can use a little bit of shorter notation just so we can go through all the different possibilities. Okay, so across the top here I'm going to put all of the m sub s values. All right, and these m sub s values can be -1, they can be 0, or they can be +1. All right, along the vertical axis, I'm going to put all the various m sub l values, which can range from -2, -1, 0, 1, and 2. All right, now, how would I get an m sub l equal to -2? All right, what are the possible combinations I could have? Well, the only way I can get to -2 if I'm limited to these values of m sub l is if I have m sub l1 equal to -1 and m sub l2 equal to -1. So if they're both equal to -1, then I can get -2. So in other words, I'm going to have all the states are going to have to be -1, -1 in order for me to have a valid state. Now, if both electrons are in the ml equals -1 p orbital, they have to be spin paired. Remember, the Pauli exclusion principle can only put 2 electrons in there. So the only possible combination I can have here is -1 plus and -1 minus as my pair of electrons. This is the only way. I cannot have anything here that would correspond to 2 spin down electrons, and I can't have anything here which would correspond to 2 spin up electrons. So these are eliminated by the Pauli exclusion principle. All right, what about m sub l equals -1? What ways can I get a -1 here? Well, the only way I can have that is if I have one of them in m sub l equals 0 and one of them in m sub l equal -1. All right, so now I'll note that I could have the first electron in 0 and the second electron in -1, or vice versa. It turns out that it doesn't matter. I should pick one of those because they're going to be the same. For example, here, to get spin equal -1, I have to have both of the electrons in a -1 and a -1/2 spin. To get 0, I have to have one in a plus spin and one in a minus spin. And to get +1, I have to have them both plus. All right, so for this particular case, if I need -1, then I have them both in a minus state, so I can have 0 minus and -1 minus. That's my one possibility. All right, I could write -1 minus and 0 minus, but that represents essentially the same state. Okay, what about for 0? Here I have one spin that's up and one that's down, so I could have 0 up and -1 down. Or I could also have the -1 up and the 0 state down. Okay, so both of these are legitimate ways to construct that. So I have to include them both in my tally. Okay, over here, both spins have to be up. So this means that my 0 and my -1 must both be plus. All right, I hope you can follow that what we're doing there. All right, now what about for this 0 state? Okay, for m sub l equals 0, I can either have both of the electrons in the m sub l equals 0, or I could have one of them in the m sub l equal +1 and one in the m sub l equal -1. So both of these combinations are possible given m sub l, big M sub l, is equal to 0. All right, so if they're both 0, I can't have two minuses. All right, so this one won't work in this first slot. And it won't work over here either. So the only one that will work in the first slot is the 1 -1, and in the last slot also 1 -1, because these have two electrons that have the same spin. So they have to be in different spatial orbitals. All right, in the middle though, however, we can do a lot of different things. For example, if I have them both in the 0, okay, then I only have one possibility, and that's plus minus, because the other one, if I put 0 minus 0 plus, that's essentially just the same state. All right, but now for the 1 and -1, I could have the 1 be plus and the -1 be minus, or I could have the opposite. I could have the 1 be minus and the -1 be plus. All right, so all three of these possibilities will give us an m sub l of 0 and an m sub s of 0. All right, when m sub l, I think you can see where we're headed. When m sub l is equal to 1, I can only have the combination of 0 and 1 together to make this. So 0 and 1 can both be negative in this particular case. Over here, I can have the 0 be positive and the 1 be negative, or I can have the 0 be negative and the 1 be positive. All right, these two combinations will work. And of course, on the last one, they're both positive, so I'm going to have that. Finally, for m sub l equals 2, again, I must have both of the m sub l's be +1. This is the only combination of m sub l values that will give me 2 here. I cannot do this because both of them would have the same spin and they would be in the same orbital, so that would violate the Pauli exclusion principle. Same thing over here. In the middle here, I'll have +1 plus and +1 minus for this. So these are all the possible combinations, all the possible microstates that I can generate for this 2-electron system. Okay, so now let's begin to put terms together. All right, well, when I have m sub l equal -2, this is implying, in this case, that L is equal to 2. So I must have m sub L equal to -2, -1, 0, 1, and 2. So I'm going to have one of each of these values corresponding L equals 2. Now notice for the only one that I have L equals -2 and +2, they are both at spin 0. So in essence, what I have is a state that is specified by those two values. All right, so that means that I must choose all of the terms from this middle column to be part of that state. Now here's where you have a little bit of freedom. It doesn't matter which ones you choose. You'll get the same result in the end. So I'll just take the first one in each of these rows to be the one that I'm going to use to represent this particular state. Okay, and I'll get to the term symbol in just a moment. Now let's look at the second possibility, and I'll use green for this, just for a little contrast. Okay, for the second one, I have a set of values of L of m sub L equal -1, 0, and 1, which means that I must have a state for L equals to 1. Now notice, though, I have S equals -1, or m sub S equals -1, 0, and 1 for each of these three m sub L equals -1, 0, and 1. So that tells me that I have also capital S equals to 1 to specify this state. All right, since I need to have all three of each of these values, that means that I'm going to use up this one, 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 and this one. Okay, all of these combinations contribute to this particular term, this particular state. All right, so I've used up most of the possibilities. The only one that's left, and I'll use blue for this one, the only one that's left is this one here. All right, which corresponds to m sub L equals 0 and m sub S equals 0. All right, so this tells me that this last term represents L equals 0, S equals 0, and we've used up the one microstate that corresponds to that. All right, so how would we construct term symbols for these things? Well, remember that the term symbol is given by 2s plus 1 Lj. All right, so let's do L equals 2, S equals 0 first. All right, in this particular case, the term symbol that I'll generate, when S is equal to 0, I'll have 2s plus 1 is 1. When L is equal to 2, that's a D state. And when I add these two together, I'll get J, so that's singlet D2. Notice that when I have a 1 up there, I call it a singlet state. If it were 2, it would be a doublet. And if it were 3, it would be a triplet, and so forth. All right, so this would be singlet D2 in this particular instance. All right, for the middle one, I've got L equal 1, S equal 1. So what kind of term do I get from that? All right, well, since S is equal to 1, 2 times 1 plus 1 is going to give me 3. So I'll have a 3, or a triplet state. When L is equal to 1, I have P. All right, now I could just add these up and get a 2. That would be fine, but that turns out to be the maximum value of J for this. J is going to range from L minus S up to L plus S, remember? So I'm going to have L minus S, which is 1 minus 1 or 0. L plus S is 1 plus 1 or 2. So I'm also going to have terms corresponding to these term symbols, where J is equal to 1 and 0. So I have 3 different terms for that. All right, finally, I'm going to have a term that corresponds to L equals 0, S equals 0, this last term here. We've already seen this. It's an easy term to work out. This is just singlet S0. So the various terms that I'm going to get for carbon include singlet D2, triplet P, 2, 1, and 0, and singlet S0. So these are the 3 terms that one would find for carbon.